Okay, so this talk is based on the joint work of myself and Professor Denis Dobkowski. Let me briefly discuss the motivation. So it's been over 100 years now that the quadrupole formula has been derived by Einstein. Its history has been quite dynamical and controversial in maybe similar fashion as the history of cosmological constant, as you all know. So Einstein believed that his result was an artifact of the linearized theory. However, already in the 1960s, by the work of Bondy, Sachs, Troutman, and others, we had already a full theory of gravitational radiation for asymptotically flat spacetimes. If it comes to experimental side, it was in the 1974 by the discovery of a binary pulsar by Holst and Taylor, when and the following years, when we are able to calculate the loss of orbital energy.
There's something funny with the sound.
But I think this is related to the position of the speaker. That he should be closer to the
It's supposed to be lower. But I think that's good. Yeah? Is that good? Yeah. Okay. So yeah, going back to 1974 and the following years, we were of orbital energy of the binary pulsar and see that it doesn't work, right? Running out of battery? No. Oh. Okay, let's give it a try. So the result was that the calculated energy of the loss, of the orbital loss, was somehow accurately equivalent to the radiated energy expected from the quadrupole formula. So nowadays we know from astrophysical and cosmological observations that there is strong evidence that the universe is expanding, and it is characterized by the positive cosmological constant, although the value is expected to be very small. And naively, one could think that the theory or the framework for positive cosmological constant is not really necessary, as we could just neglect it and use the known framework for the vanishing lambda. However, the structure for the conformal structure of the Cedar and Minkowski spacetimes are quite different. And taking the limit is at times quite a subtle thing. In particular, some of the observable quantities may be discontinuous, especially if you consider various coordinate systems. So our goal here is to calculate the energy flux carried by the gravitational waves. So generalize the non-Einstein quadrupole formula. And here, instead of the conformal boundary known from Minkowski space, now we will use the cosmological horizon. And then we will check whether our result retrieves the famous Einstein quadrupole formula in the lambda equals 3. Okay, so let's start with the overall setup. We consider the conformal Penrose diagram of the Cedar space. Down here, as already noted, the infinity is space-like, not null. Cosmological horizon is denoted by H. E plus is the past boundary. And we consider this time-changing source here at the origin, emitting gravitational radiation. All the action will take place in this future Poincare patch. A similar setup has been considered by Ashtekar and his collaborators, where they calculated the energy flux passing through the space like infinity. However, in our case, we're just focused on the cosmological horizon, and therefore this left pink triangle is where all the interesting stuff happens. So, similarly as in perturbed Minkowski spacetime, we consider here the metric G. Here the background metric will be the de Sitter metric, and gamma is a perturbation, epsilon is a smallness parameter. We first work in the coordinates such that this Sitter spacetime looks a bit like Minkowski with a conformal factor. Here h is just the Hubble parameter, so it's proportional to the square root of lambda. Now we can express the linearized field equation in terms of this trace reverse metric perturbation gamma bar. The form of this equation is simpler this way. However, we then apply a gauge condition, so like a generalization of the Lorentz gauge. Here this vector n is just a future pointing unit normal to the cosmological slices that are defined by eta equal constant. We may yet simplify the equations even more by introducing the rescaled trace reversed perturbation chi bar, defined in the following way. And then to solve this set of equations, it is convenient to also perform a decomposition of chi bar and also the linearized source T, matter source. Here we'll have chi bar, which is similar to the trace of chi bar apart from the sign here, which would be minus in terms of the trace. Chi A is just a space and time component of the trace reverse perturbation, whereas chi AB is a space-based component. Similarly, we do for the matter source. Here Q with naught is just a spatial metric on the cosmological slices. So now the Einstein equations may be split into three equations, and their solutions may be obtained using the scalar green functions. The first two of them are easily solved in a similar fashion. The last one has a similar term as the other ones. However, it also, because of this partial eta operator, it also depends on the past of the source up to the retarded time eta is defined in the standard way. So the full description of the derivation, you may see the paper by De Vega, Ramirez, and Sanchez from 1998. Okay, so how about the approximations and assumptions that we are using here? First of all, we assume that there's no incoming radiation from this past Poincare patch. Second assumption is quite technical and could be relaxed, although it's quite helpful in the calculations. So we assume that the system is stationary at distant past and distant future. So it's only dynamical for a finite period of time. Then the third assumption is that the physical size of the source is bounded. We apply this assumption because we want the system to remain compact regardless of the expansion of the universe. The fourth assumption is that the cosmological constant is very small and that makes this cosmological horizon very distant from the matter source. And finally, a slow motion approximation approximation so that the velocity of the source is more speed of light. Okay, so our goal is to express the retarded solution K-B in terms of the quadrupole moments. Here, notice first that these coordinates eta, x, y, z are not compatible for taking the limit to lambda going to 0, as this term, this denominator, blows up as h is proportional to the square root of lambda. So we introduce a new time coordinate t in the following way, and then our metric, background metric, is of the following form, and taking a limit is just straightforward and retrieves the Minkowski metric. So in these coordinates, in t, x, y, z coordinates, we express this retarded solution in terms of the quadrupole moments, so that they are written here up to the square, up to the terms quadratic in h, so linear in lambda. And the quadrupole mass and pressure moments are defined in the standard way, where the density x bar here is the physical distance of a point in space from the origin, and pi is the pressure in the r direction. Okay, so now we used the formula that was derived for energy flux passing through the null surface by Chandrasekaran, Flanagan, and Prabhu. They used the Wald-Zupas formalism and derived the following expression. Here L is the time translation. In our case, this will be the vector field T. And this vector field is in the limit as lambda goes to 0, it recovers the time translation from Minkowski spacetime. And if you consider the time translation killing vector field in Schwarzschild, the Sitter spacetime, and take a limit as the Schwarzschild mass goes to 0, then you retrieve exactly this vector field T that we consider here. And it's a null surface, so obviously in our case we choose it to be the cosmological horizon, which is defined by this relation between R and T. And then sigma and theta is just the shear and expansion of the vector field T. Okay, so notice that we are considering here the perturbed horizon. Okay, so in a generic case, this won't be a null surface. So what we have to do is to sustain its null character, we have to introduce yet another gauge fixing in such a way that with respect to this new geometry, this vector field T will be null and therefore on the horizon, and therefore the horizon will remain its null character. So it may be interpreted as a deformation procedure for the cosmological horizon, and making it a null surface even with respect to the perturbed geometry. Okay, so the results that we obtained by expressing the shear and expansion in terms of the quadrupole moments and integrating over the angles is the following expression for the energy flux. Here we expressed it in the linear, up to the linear order in H. And also, to make it more elegant, we introduced the traceless quadrupole moments, which I denote by lowercase q. Notice that taking the limit of this expression is quite straightforward. We only need to put h equal to 0, and therefore this recovers the famous expression for Einstein quadrupole formula in exactly the same way as for instance, presented in Wald's book. Notice that for non-vanishing cosmological constant, there is not only the mass quadrupole moment, but also the pressure quadrupole moment that has an impact on the overall value of this energy flux. Okay, so there are a few other approaches to calculating quantity formula for non-vanishing cosmological constant. The first one that I want to comment on was also derived for the positive cosmological constant and calculated on the cosmological horizon. This was obtained by Hock and Birmani in 2018. And there is a symplectic current density in the covariant phase space to obtain their result. They also, as you may see, they also expressed their formula in a TT projection, which I'll comment on later. These are maybe expressed in terms of the quadrupole moments, and the dots indicate the mean derivatives with respect to the vector field T. When we integrate this expression over the angles and expand it for small values of cosmological constant, we actually obtain a similar formula that we had obtained. However, there is this difference of a factor standing by these terms. I'll comment on this in a moment. And then the other formula obtained by Ashtekar in 2015, as I already mentioned, is a quadruple formula calculated on Scri. And here it is written in terms of the also transverse traceless fields. However, here this TT is a gauge TT, which is significantly different for non-asymptotically flat spacetimes. In Minkowski spacetimes they do coincide. However, here in positive lambda case, it is not necessarily true and needs to be further examined. So notice that in our case, this source that we consider was of a compact support. It could be also a source of a periodic nature, and here this term, which I told you that does not coincide with the result obtained by Hock and Birmani, this term may be written as a total time derivative of a squared term here, and when integrated over time, it actually vanishes. So we see that it's actually gauge variant term, and our result really coincides with the formula obtained by Hock and Birmani. What is left to be checked is whether the formula obtained by Ashtekar coincides with our formula, but from the symplectic geometry theory we know that those two should coincide. A brief comment on the TT gauge and TT projection, as it is often stressed by Ashtekar that these two notions, they don't coincide. So here the TT gauge is a decomposition for any spatial rank 2 symmetric tensor into some irreducible components. So the TT, ATT corresponds to the transverse traceless part and satisfies divergence and traceless equations. BT is also transverse, and such decomposition extracts the gauge invariant physical components of the field A. Extracting these TT components is a highly non-trivial task, and has been performed in some simplified cases, for instance by Bonga and Hasban recently for the circular orbit binary systems. On the other hand, the TT projection is a quite simpler thing to do in calculations. So we just introduce the projection operator and then construct lambda operator, and to extract the TT the transverse trace is part of A. We just contract this operator lambda with rank 2 tensor. So as already noted, these two notions are they do coincide only in cases of asymptotically flat metrics, although at some situations they may also be similar in some approximations, even in lambda greater than 0. It remains to be shown, however, that the three quadruple formulas, they all coincide regardless of the notion of TT. That is still an ongoing project. Okay, so thank you for your attention.
Thank you. Now we have time for questions. And then? Okay.
Put some numbers for those detections that are known to us and for the value of H that we know what would be the effect.
Yeah.
10 to minus 4, 10 to minus 6.
Yes, also we know that the quadratic formula that was derived by Einstein was already accurate with this quite good measurements that we are having right now. It was accurate up to 0.3%. So it's already quite a good result. And adding cosmological constant is actually, in this case, in the case of quadruple formula, is quite negligible, although it is important to see its derivation, as the limit is not always so trivial to be taken. Yeah.
More questions? If not, let's start.